So good afternoon everyone. So welcome to another session on small talks. So today we are going to discuss on the topic threads versus processes. So this has been one of the very famous interview questions. So and also I hope we all have gone through these stuff in university as well. So or under operating system. So I'm not gonna go into much details, but this would be a refresher for you guys as well. So I'll try to briefly touch the concepts and get you guys to what I want to discuss. So first, let's see what is a process. So we all know process is a executing instance of a program or application. So basically, process, there is something we need to keep in mind here. So process in an operating system environment, there is thing called the process control block, which holds the information where it needs to control the process, the priority, the process ID, state, CPU registers, all those stuff are there within the process control block. And also there are memory locations and the stack of the process within the operating system. Then we'll move on to a thread. So thread is basically a path of execution within a process. So thread is also, there can be multiple threads within a process, and thread also has these specific set of controlling structures. So we'll go into those details in the next slide, in the coming slides. So we'll just little bit go into how threads work. So I'll take the process creation using a fork system call. So whenever we issue a fork system call within the operating system, it will create a replica, a full replica of the process, or we call it the parent process, or whatever the process that is initiating this call. So then replica would contain the page table and the kernel stack of the parent process, and a new PCB or the process control block is created for this new process. In that case, the child process or the newly created process, the new PCB will have the state from new, because that what that indicates is that this particular process ID is already taken, you can't reuse again. So that's the indication to the OS. Then it will, once all the things are PCB is created, it will go to the ready state. So then the process is put into the ready queue of the kernel, so that it will get the time to execution time from the kernel itself. So whenever something happens, or whenever we whenever that new process or the child process writes something, it will be on copy on write method, which means that as I mentioned earlier, there's a copy of the parent processor's page table and the kernel stack. Whenever the child process writes something into the memory, that value will be copied and then it will be written. In that case, the parent process will not, the memory of the parent process will not be touched. So basically in a Linux or the Unix system, the first process or the initial process is known as the super parent. So which is, it is the process, the execution, the executable file is in the sbin init, and it is created by the kernel. So typically what it does is like it executes few of the scripts within this etc initd folder. So the process, in the process termination, there are two types of process terminations. One is the voluntary, involuntary. Voluntary termination is that it indicates that whatever the corresponding task is done within the process, and it will give the control to the parent, and it will return the actually it will state the status code of the whatever the status code of the child process in the memory. Then the other one is the involuntary termination, which indicates that it has been killed by either the OS or by some other process. So basically in the involuntary termination, a signal will be sent to that child process, which will kill the child process. So basically these there are a couple of those signals are basically integers. So one of few examples are sigterm, sigquit. So those would make the child process terminated. So basically, for the process communication, there are a few mechanisms currently in the OS. One is the shared memory. So in the shared memory way of communication, these are the functions it uses: SHM get, SHM allocate, and deallocate. So what this does is, like, within the kernels, within the OS, it allocates a memory space which will be shared. So initial method would create that shared memory space, and the other two, the first one would allocate it to a particular process, and the second one would be deallocate. It is basically a bit faster than the other methods because that shared memory space can be used as its own memory space. But the thing is, there are concerns that particular shared memory blocks need to be synchronized, and all those complexities need to be handled by the processors. Then the other mechanisms, such as message passing. So in the message passing, there's a shared memory location created in the kernel. Therefore, all the request has to go through the kernel. So since if a process wants to communicate to another process, so it has to go to the kernel. Because of that, the execution has to be handed over to the kernel, and it is controlled by the kernel, so it is comparatively slow. Then there are pipes. Pipe is a unidirectional data flow from a parent to a child process. And the signals are, as I mentioned earlier, basically signals are integers. That it is also unidirectional. It is also used in such cases. So that is how basically a process works. In a thread, when it comes to thread operations, so basically threads are very inexpensive to create and destroy. We'll see why it is that, because since the threads reside on a process, so when a new thread is created, the threads are sharing the code section and the data section and the other operating system resources. Those items will be shared among the threads, but only a new stack and register set and the program counter will be created for a new thread. Because of that, the thread's context is small, so that it can easily create a new thread, and it can easily, without much expense, it can terminate a new thread, and also the context switching is also a bit easy. So, but the thing is, like, since the memory locations and some of those data sections and all are shared, so it needs to be synchronized and properly maintained. Otherwise, there can be situations like locks, deadlocks, and those sort of situations. So because of that, if I summarize the whole thing, so when it comes to a process, the time for execution is faster. Time for creation is costly, or it takes more time. In threads, it's less time. So termination is also same. The communication is less efficient on processors, and threads, it's easier. Memory is isolated, which means it's not shared. In threads, it's shared. So then I come to the conclusion. So some people might agree on this, or some people might not. So it would be depending on the case, but basically processors would be good for tasks where there are enough work or the sufficient work available to be done for a longer period of time continuously, so that that process will not be idle. And also that whatever the task should not require much communication between other tasks, and the coordination or the controlled by something else or some other task. And also if a task has less context switching and it can independently work, then a process would be a good choice for that one. If a task has less work to do and the lifespan is small, it requires communication between other tasks, the context switching, and it requires data sharing or the resource sharing between tasks. Maybe thread would be a good option in that case. So basically, you can make the decision depending on type of work or the type of task you need to do, then the lifetime, then how the scheduling should work, then depending on the resource sharing, data sharing, communication, and the controlling, synchronization, coordination between the tasks. So with considering these factors, you can decide whether to go for a thread or a process. So that is pretty much the what I want to discuss. Yeah, so then thank you.